So we're continuing on with what we talked about last time, double integrals. And today's stuff, we're gonna look at 14.3 and 14.4, good sections to go over because you're gonna get some practice doing double integrals, okay? We're gonna talk a little bit about doing them in polar, and then we'll just look at some applications. And then honestly, I don't think I'm gonna talk for very long today. We're gonna spend most of our time working problems and getting some practice with this stuff, okay? We already we talked about polar earlier when we talked about cylindrical coordinates, right? Cylindrical coordinates are polar plus the z-axis, so they're polar in 3D. So we've actually talked about this stuff, so I'm not going to beat this part to death. But remember, when we want to use polar is when we have a region that is symmetric around the origin, something that's circular. Okay, so we have our polar transformations. All right, so you're going to want to know those because that's how you transfer an integral into polar. And we'll take a look at an example here in a little bit. And we don't need to do that because you guys have already had some practice with that. But these are the kind of regions that would indicate we'd want to use polar. If you got something in the XY plane that is circular, polar might be good. But here, if you have something like this where it's a disk, you'll definitely want to use polar because this would be ours just going from 4 to 6. To do this this one in rectangular is a mess. This one in rectangular is not so bad, but it may be hard to solve by hand. All right, so we'll look at that here in just a second. So, and you saw the stuff in the video. Basically, what we're doing with polar is it makes some integrals easier to deal with. So we need to decide when we want to do that. Well, like we said, when the region is circular, all you need are your transformations. X is r cosine theta, y is r sine theta, and x squared plus y squared equals r squared. Those three things. And then there's the dA component, and you saw this in the video, so I won't bore you with it again. But the dA, which is like the dx dy or the dy dx, when we convert to polar, because the way the region is set up, it's like a cut off slice of a pie. We're actually using the arc length of that piece. Well, arc length is the radius times the angle it subtends. So that puts an extra r in our dA when we go to integrate, okay? And it's just because we're doing the arc length. So we have our transformations. If you have any x's in there, it's r cosine theta. Any y's in there, it's r sine theta. And if you have an x squared plus y squared, it's r squared. We do not want to have x's and y's in there if we're integrating with respect to polar, because we're integrating with respect to r and theta. And the dA is either going to be r dr d theta or r d theta dr. What you want to take from this is if you're doing the integral, if you're converting to polar, remember to put an extra r in your integrand. Otherwise, it won't come out right. Okay, that's really what's going on with polar. So let's take a look at an example. I'm going to do this one here. Let's do the second one. The volume under the plane z equals x, above the disk of radius 3, bounded by x greater than or equal to 0. And we'll look at it both in rectangular and polar so we can decide what we like better. Okay, so x is greater than or equal to 0. So we're only looking at the right-hand side of the circle. And let's talk about it in rectangular first. Now we're looking under the plane z equals x, right? So the function is just x. So it's going to be a double integral, and then x, and then we got to decide if we want to do dx first or if we want to do dy first. Now, if you want to calculate this one by hand, you're going to want to do dx. You're going to want to integrate, excuse me, with respect to y first. And I'll show you why. If we think about this region here, part of a circle, well, we know that the equation of a whole circle is x squared plus y squared, in this case, equals 9, or 3 squared. This is going to be something you're going to get really used to in these next couple of sections. Is we're going to have a lot of regions that are circular or spherical, so you get really used to dealing with these equations. So I want to integrate with respect to y first, and it's because of that extra x. So if I integrate with respect to y first, that means I'm solving this for y. So y equals plus or minus square root of 9 minus x squared. Okay, minus for the bottom half. So that part right there is the y equals negative square root of 9 minus x squared. That'll give us the negative y values. This guy here is going to be y equals square root of 9 minus x squared. So those are our limits. Negative square root of 9 minus x squared up to square root of 9 minus x squared. Okay, because we're going from this curve to this curve. Inside limits can be in terms of one variable. The outside limits have to be constants. Well, now we're just going to integrate with respect to x, and we're going to go there, which is 0, 0, 0. Very nice. Okay. Now, this is actually a doable integral by hand. So let's go ahead and do it for practice. So we integrate with respect to y. So 0 to 3, x times y, and y is going to go from negative square root of 9 minus x squared to square root of 9 minus x squared. And then we'll integrate with respect to x. That's okay. You know, we can put an x in there. We're going to integrate with respect to x still. Fundamental theorem, upper minus lower, right? So basically what we're going to have, 0 to 3, x, we're going to have this minus this. Well, we're subtracting a negative. So we're going to end up with 2 times the square root of 9 minus x squared. That's from the fundamental theorem of calculus. Okay, we kind of combined a couple steps there just because I know I'm going to run out of room if I don't. Okay. Here's why we can actually still do this one, because the function was x. And without that x, this is still doable, but you have to do it as area under the curve. Now we can do it as a u sub. So u equals x squared, du equals 2x dx. All right, there's my 2x dx. Actually, let's have u be 9 minus x squared. Might as well get that all in there, which will bring in a negative, not a big deal. So we do need a negative. So now we have a negative 2x dx. So we have negative the interval from 0 to 3 of square root of u. So u to the 1/2 du. Oh, and actually, let's do this too. I'm a big fan of changing the limits on u substitution. So when this was a 0, put in 0 for x, you get 9 minus 0. So the lower limit is 9, the upper limit will come out to be 0 when you plug it 3 in. That way we don't have to sub back. I'm a big fan of changing the limits, you don't have to. All right, antiderivative is, so we get negative 2/3 u to the 3/2 from 9 to 0. So first part's going to be 0 minus a negative. So minus negative 2/3, 9 to the 3/2. All right. That's the square root of 9, which is 3, cubed, which is 27, times 2/3, which is 18. Okay. This one's doable by hand. I mean, I've chosen a function, so it would be. Okay, that's in rectangular. That's the kind of stuff we were doing last week. Now let's talk about doing it in polar. All right, so in polar, don't know how the markers are dead when we're the only ones who use this room. Not sure. Let's see if we can use it better. All right, did you already use it? That's right. This. All right, that's better. Okay. Now the nice thing about polar is it handles circles very easily. Okay, because all we have to do is take into account, okay, the radius goes from 0 to 3, and the angle goes from negative pi over 2 to pi over 2. So 0 to 3, negative pi over 2 to pi over 2, and we could actually switch that order if we wanted to, because they're both constants. Now, let's talk about what goes inside. Well, there's an x in there that has to be transformed. Remember, x is r cosine theta. So we get an r cosine theta, and that came from the x, right? That was the x from there. Now this part, this is that dA we were talking about. That's where we have to put in the extra r. So r, and I'm doing dr d theta. So that's that extra r that you have to put in when you integrate in polar. Okay, it is just part of this. And now we get to calculate. Now we've got the r times r, so that would be an r squared. So the antiderivative of that, so we're going to have negative pi over 2 to pi over 2. So again, kind of combining two steps. We're going to have r cubed over 3 cosine theta, because that's a constant with respect to r. And then r is going from 0 to 3. And then we'll still integrate with respect to theta. So I can put the 3 in. 3 cubed again is 27. Divided by 3 is 9. Let's pull the 9 out. So basically now we're just down to this 9 from negative pi over 2 to pi over 2 of cosine theta d theta. Antiderivative of cosine is sine. Let's got the 9. So 9 sine theta, negative pi over 2 to pi over 2. 9. So we'll have sine of pi over 2 minus sine of negative pi over 2. So 1 minus a negative 1 is 2 times 9. And there's 18. Same thing either way. You know, we can debate which of those was easier to do. But as you can imagine, because when we do rectangular coordinates, anytime there's a circle, it's going to involve a radical of the radius squared minus the variable. In general, polar will be easier. This one would have worked out okay. It worked out nice because we had the extra x in there, so we could do a u sub. Would have worked out okay because we were doing from 0 to 3. But if we didn't have, if our function was something different, or we were not doing a nice symmetric interval, this thing would have been kind of messy and rectangular.
Why is it r cubed over 3 instead of r squared over 2?
R times r is r squared, and then we take the antiderivative. I just skipped the step of multiplying them together, just because I knew I was going to run out of room. That's all. Yeah, I did skip a couple of steps. So yeah, typically we multiply the r's together first, you know, combine all like terms, then integrate.
So that extra r is applies.
Yep. It acts just like any other, it acts just like a regular r. So you have to treat it as such. So if you have another r term in there, you got to make sure you multiply those together first. Other questions? Okay, you're going to get to practice that here shortly. So I think it's going to go pretty smooth. And again, it's pretty obvious when you're going to use polar. You know, your region will be circular, semicircular, something like that. And the same thing will go when we use cylindrical in triple integrals, which we're not getting to until next week, but this is why you want to start getting this stuff down now, because what we do next week is go to triple integrals. And the better you are at double integrals, the easier triple integrals will be. All right. This is another section I'm not going to spend a ton of time on, applications of double integrals, because now what you're going to do in 14.4 is set up double integrals given situations that involve double integrals. So this is now just taking the situation you're given, setting up the double integral, and then doing what you're doing in 14.1, 2, and 3, which is calculating double integrals, either in rectangular coordinates or if it's advantageous in polar coordinates. So I'm just going to go through some of the applications, but you saw these in the videos. We already know double integrals can be used to find areas. You know, if you set the function to be 1, then what the double integral is doing is finding the area of this region. Same thing would go with this example. If this function was just set to be 1, then we'd actually just be finding the area of that half circle. Total mass. So if you have a varying density over your surface, then integrating over that density would give the total mass of that surface. Right? Very similar idea to what you saw in Calc 2. And if we can do total mass, we can do center of mass. All right, do not worry about memorizing these formulas. You know, you guys can use your note cards for them. I don't usually put center. I wouldn't put center of mass on an exam anyways. This would be more like a take-home type of thing. But you know, we can do center of mass. It's again very similar idea to what you were doing in Calc 1, except in Calc 1 you were looking at the moment in either the x direction or the y direction. Now we can look at the moment in the x and y direction in a two-dimensional surface. And then just a note of being careful, just because of the way it works. M sub y is the tendency to go about the y-axis, which means it's actually in terms of x. So it's actually used to find x bar. So and it's something, like I said, you're not memorizing these formulas, so it's something you would have on your note sheet anyways. But just, I always like to point that out because it can be a little confusing that M sub y gets used to find x bar. And the reason is because we think of it as the moment or the tendency to go around the y-axis, right? Well, if you're going around the y-axis, you're changing the x's. Total charge. All right, so if you've got a charge density, doing the double integral will give you the total charge on the surface. And again, you know, these aren't going to be, they're going to be really obvious because you're going to see in the problem, oh, I'm given a charge density right here. That's what I'm integrating over. And then most of our work, or most of what we're going to do, is figuring out what the region is and setting up the limits. It's going to be pretty obvious what you're integrating over most of the time. Probability. This is another one that involves double integral. So if you have two random variables, x and y, then you get a probability that creates what's called a probability density function. And those can be integrated over to actually calculate the probability. So if you take any calculus-based statistics courses, a lot of times you actually don't do these calculations yourself. They've already been calculated in tables, and you base off of your A, B, and C, and D, you look up in the table what the probabilities are. Well, actually, nowadays you probably don't look them up in tables anymore either. You probably just put it in the computer. But again, the key is setting it up. So that's going to be the thing with these application problems. Probably the actual integration you're going to find not any more difficult than what you're doing in 14.2 and 14.3. The big thing is going to be setting them up, because that's what we do in practice, right? We can always use a computer to solve a double integral, but the computer can't set it up given our situation. Is probability the last one? No. Oh yeah. I'm gonna leave that because I think that might be on the worksheet. So But basically you got this probability density function and you're integrating over this rectangle that would make up your limits. Okay. So again, I kind of just went through some of the applications that we would see depending on what route you're heading after this. There's going to be other applications. You'll see them in the homework. But what we're doing, it's going to be really obvious that, hey, oh, I want to use a double integral here. I know what I'm integrating over. I'm integrating over this charge density. Oh, what's my region? So we're going to be, most of our analysis is going to be in figuring out the region of the surfaces so that we can get our limits. Is it better to do it in rectangular or polar? Okay. If you guys don't have any other questions, that was all I wanted to talk about. Like I said, I wanted to spend more time letting you guys practice double integrals. So I'm going to give out the worksheet and let the live online folks work with Professor Tar. Let's see.